Hello everyone, my name is Nikita Umerov, and in this video I will show you how to integrate functions really easy. I promise. You're gonna love integration as much as I do. To do this, I assume that the integral is an operation. You may think that the integral is something else, but 500 people who downloaded my paper on Zenodo seem to agree with me. I also made a video about that paper in which you can find the theory for what we're gonna do today. This video is also based on my recent paper on algebraic integral for dummies. You can also find it on Zenodo. One of the main methods of integration is the substitution method, which is usually the most difficult for students. Today, I will show you how to integrate functions using a new algebraic method instead of the substitution method. Probably in the future I will make another video about integration by parts, but that is even easier than we're gonna do today. Let's begin. To solve integrals, you need to know what addition, multiplication, and composition are. The first two you probably know from school, but not everyone knows about composition. And that's okay. Composition is just an operation like addition and multiplication. Probably later I will make a separate video about composition, but for now the important thing for us is that there exists an object x, which is a compositional identity. F composition x is equal to f. Just like 1 is the multiplicative identity, f times 1 is equal to f. And 0 is the additive identity. F plus 0 is equal to f. Soon, we will see how composition works in practice by solving concrete integrals. Also, we assume that any object in our system has a compositional inverse. We denote it with a negative first power. F composition f negative 1 is equal to x. If we want to write the multiplicative inverse, we simply write 1 over f. F times 1 over f is equal to 1. All other powers we denote as usual. The additive inverse we also write as usual. F minus f is equal to 0. And so, we have everything we need to define the integral axioms. Well, the integral is usually denoted as integral f dg. But instead of that, we will write the integral as an operation at triangle. F integral g. That satisfies the following axioms. First, identity axiom. 1 integral f is equal to f. 1 is multiplicative identity. Second, associativity axiom. F g integral h is equal to f integral g integral h. In a sense, we move g through the integral to the right or to the left, depending on which side you read from. Next, the most important axiom, the integral axiom. It turns out that composition is distributive over the integral. That is, f integral g composition h is equal to f composition h integral g composition h. This is nothing but the expanding brackets rule from elementary school. The last axiom is that the integral is a bilinear operation. You can read about bilinearity on the internet. I only write out linearity in the second argument, which is what we need today. F integral alpha g is equal to alpha f integral g, where alpha is some number. Note that we can multiply our objects by numbers, and f integral g plus h is equal to f integral g plus f integral h. We will also need two more special objects. So far, we have 0, 1, and x. The units for our operations. The integral doesn't really have a unit like that. Instead, it has an exponential object. When you integrate it with x, it stays the same. Exponent integral x is equal to exponent. In a way, it's a weak unit. The compositional inverse of the exponent we call the logarithm. I remind that compositional inverse means exponent composition logarithm is equal to x. That's everything we need to solve integrals today. Nothing more. I can't wait. Let's get started. The first object we're going to integrate is 1 over x. For the first time, I wrote the integral in classical notation. Then we will forget it like a bad dream. 1 over x integral x. Let's think about how we could solve this. We have associativity and the identity axiom. It would be great to represent x as the integral of x with something. So we could move x to the left and get a 1 on the left. You will see what I mean in a moment. This is exactly the case where we need the exponential and the logarithm. Remember that x can be written as a composition of the exponent and the logarithm. X is equal to exponent composition logarithm. By definition, exponent is equal to exponent integral x. Exponent integral x composition logarithm. Notice that here we use the integral axiom for the first time. That is the expanding brackets rule. So it is equal exponent composition logarithm integral x composition logarithm. Here we see again the composition of the exponential and the logarithm, which is equal to x. Integral and composition with x doesn't change the logarithm. That is, x is equal to x integral logarithm. X equal to x integral logarithm. And we rewrite example 1 using that fact. 1 over x integral x integral logarithm. And we see that we can move x to the left through the integral using associativity. We get 1 over x times x integral logarithm, which is obviously equal to 1 integral logarithm. 1 integral logarithm. And by identity axiom, this is just logarithm. Example 2. Let's integrate 1 over x times logarithm. By associativity, we move 1 over x to the right through the integral. 1 over logarithm integral 1 over x integral x. In the previous example, we found out that the right side is just their logarithm. 1 over logarithm integral logarithm. Here, we need to see that 1 over logarithm is a composition. 1 over x composition logarithm. And we add x to the left of the logarithm. X composition logarithm. And we see that we can apply the integral axiom pulling the logarithm out of the brackets. 1 over x integral x composition logarithm. And again, we know that the integral of 1 over x is equal to logarithm. We get logarithm composition logarithm. Or in standard notation, logarithm of x. That was easy. The last example. Here, we're gonna use linearity with respect to the second argument. Also, implicitly we will use the additivity of the exponent, or the fact that the exponent is a homomorphism. The point is that the integration of power functions is uniquely determined by this property. You can find the details in my recent paper unmentioned at the beginning of this video. Let's move x squared to the right by associativity. X cubed plus 1 to the 1/3 integral x squared integral x. Integrating the x squared object implicitly uses the additivity of the exponent. I'm not going into details. You can find them in my recent paper. X cubed plus 1 to the 1/3 integral 1 over 3 x cubed. We have integrated x squared. Now, let's use linearity with respect to the second argument. First, we can pull out the 1 over 3, and second, due to linearity, we can add plus 1 to the x cubed on the right hand side. 1 over 3 x cubed plus 1 to the 1/3 integral x cubed plus 1. If we expand x3 plus 1 here using linearity, we get an integral with a 1 on the right. It's well-known fact that the linear maps map numbers to 0, which is why we can do this. And now you need to see that what is written on the left-hand side is a composition of objects. 1/3 x to the 1/3 composition x cubed plus 1 integral x cubed plus 1. But now we can use the integral axiom, pulling x3 plus 1 out of the brackets. 1/3 x to the 1/3 integral x composition x cubed plus 1. We integrate x to the 1/3 in the usual way. You can find details in my recent paper. And we get 1/3 3/4 x to the 4/3 composition x cubed plus 1, which is equal to 1/4 x cubed plus 1 to the 4/3. You can check the internet to verify that this is correct result. From these examples, we can see that the process of integration by substitution actually boils down to applying just two axioms, associativity and the integral axiom. It's very easy and exciting. And with that, we are done with math for today. In conclusion, I want to express my support and solidarity with Grigory Perelman. Perelman is my hero because he is the first person who openly challenged the academic system. He rejected their money because academia has failed. Perelman proved the Poincare conjecture, but the main thing he proved that we are not crazy. They are crazy, those who trying to monopolize truth itself. Actually, there are very few people who really understand what is going on today. Why do we still have all these problems in the 21st century? But there are such people. They are mostly philosophers, some of the smartest people. For example, you can read Paul Feyerabend, Stephen Toulmin, or Georgia Agamben. In the description I will add a list of some of these people and their books. The truth is that the freedom of religion we hear so much about is an illusion, while academia is an international religious organization. If it had existed in the time of Galileo Galilei, Newton, or even Maxwell, we would never have known what scientific progress is. We would still be in the Middle Ages, because academia would stop them. Academia is not science, don't confuse them. This system is relatively young, only about 100 years ago. This is a system of Karl Popper, Russell, and Dawkins, propagandists, not scientists. Popper and Russell did nothing for science, absolutely nothing, only harm. Don't listen to what they tell in their churches. Some science still exists only because academia hasn't killed it yet, but they're trying. Academia and the modern education system are anti-science. They don't teach us rhetoric. They don't teach us critical thinking. They don't teach us how to argue with a professor. They teach us to obey him during exams. Academia is based on submission, not on free collaboration, so it cannot be scientific. I understood what an integral is only because I don't have an academic education. If I had studied there, I wouldn't have done it, I'm sure. Academia is anti-scientific. At the moment, I'm working on a book in which I explain why academia is the main problem of the modern world, and where they might lead us. Actually, we're almost there, but I know how to fix it all. I know how to restore science, because today it's almost dead. I propose practical steps to change the situation, for you personally, for each of us. It's really not that hard. In this work, I need moral support, and financial support in particular. Recently, academia offered me a job, and of course I refused. I don't want to become a saint of their church, and I openly say that I have nothing to do with it. I'd rather die than work for them. In the description of this video, you will find ways to support my sociological and mathematical work, or simply like this video to show me that I'm not alone. Thank you.